and we're tidally locked. So we have this side is always day, but then on the reverse side, it's always night. So the ice is always in darkness for this planet. Let me just send that guy up there. And I put a small base there just for laugh. So there are other options. This was an interesting planet as well. And I have another 3D model. And this was a planet that was discovered fairly recently. I want to put this where you guys can still see the video. I'll put it up here and we'll bring it down. So this was a recent discovery. Let's just play the video, it'll tell us. Called LP 79118d. It's an Earth-sized planet. It's right on the inner edge of the habitable zone. And it is tidally locked. However, there is another planet in this same system, which is also pulling on LP 79118d. And what that other planet does is it makes its orbit slightly elliptical. And like we saw for Jupiter's moons, if you have a slightly elliptical orbit, you get kind of squeezed by the star or the planet's gravity. And this might make a very volcanic world, perhaps a little bit like the innermost world Io, an innermost moon Io around Jupiter. And if you have a very volcanic world, maybe the spewing of gases back into the atmosphere could actually replace any lost atmosphere if it was freezing out. Sorry, Esmond, could you mute? Thank you. And that might be a way of maintaining the atmosphere. So you would end up with a highly volcanic planet, but you would you might be able to preserve on the night side enough atmosphere that you could possibly of the star due to its gravitational tug. And as you try to orbit the star's gravity sort of tugs on that bulge. And what you end up with is always the same size of the planet facing that star. And that's exactly the same as the moon. The same size of the moon always faces the Earth. Both cases are called tidal locking. So when you have a planet, what you end up with is one side of perpetual day, where the sun never sets, and one side of eternal night. Now, if we assume they could support life, let's assume they're vaguely Earth-like, you still have a very un-Earth-like situation where you have these two hemispheres of day and night just crossing across the planet. So whether a planet can survive this, or more to the point, whether any oceans on the planet can survive this, depends very much on whether you can sort out that heat difference. If you cannot sort out that heat difference, oops, sorry.
I'll take this one to start. So if Iron Man is real, it is a robot. Why? First of all, it is a mechanical electrical device. Second, it is programmable. There's a scene in the movie, I don't know, the Tony Stark is programming. Also, you can see it has a like this kind of VR, or it's a AR, or mixed R something. And it has perception because it has sensors to understand experiments, and it also can take actions. So Iron Man is a robot. Let's see if I can move this. Yeah. Okay. Cool. Let's continue. How about Boston Dynamics spot? So does anybody know what Boston Dynamics is? Or have you heard of Boston Dynamics? Raise your hand or not. Yes, I see someone raised their hand. Yes, cool. So if you don't see the 3D model, just turn around, you will see that in the center, okay? This one is a Boston Dynamics, the yellow robot. I'm not sure if all of you can see that. Let me know if you don't. And this is not the real size, it is zoomed in. And it is a legged robot. It is a robot, and it has 4 legs. It's kind of like a dog, and it has 4 legs, and it has a robotic arm on the top. Then is a robotic arm, so it can operate something, can pick up something, or can push the door, open the door. And it has sensors. In the front, it has some sensor. If you can come here, and if you can see this huge black something, this one, uh, they have integrated sensors like cameras and other kind of sensors that we will talk about in our uh, we will talk about that tomorrow. Like there are some integrated sensors here. So Boston Dynamics Spot is the name of this Lego robot. It is a robot because it has mechanical mechanism, and it has computer, so you can uh, it's an electric device, and you can program it, and it has sensors to perceive the world, and also have robotic arm to operate objects. So yeah, uh, Spot is a robot. Let's continue. See our slide. Our smartphone.
I'm gonna handle the data that my satellite is producing, right? So I need commands to manage that, right? So of course, I need a certain protocol and a specific protocol that I have to create in order for my mission to fulfill, and that command and data handling needs to work closely with the attitude and determination and control. Because the attitude, determination, and control basically is the one that puts the satellite in the right position for me to take the data. Because if it's in the wrong position, then it will take the wrong data, right? I see that it's 14:59, guys. I don't know if you have any questions. I would like to leave it here, and then tomorrow we will continue with these same slides, because I think our next lecturer is already here. But then in the meantime, please feel free to make any questions. More than happy.
See, there's this large area right there. That's where the Kepler survey was. Picked one spot and looked at it very, very carefully to find as many planets there as it could. Thousands of them. That's a lot of planets. But we're only just barely scratching the surface of what we can find. There's so much more to find out there, and it is so cool. Particularly accurate. All the planets aren't on those orbits. Those aren't even the right planets. So this is just a solar system. And if it's tilted like this, you would imagine that we could do direct imaging of maybe the outside planets here. And we'd also be able to look for microlensing type stuff. If it's tilted like this, then you'd be able to see planets passing directly in front of the star, and with that be able to detect them with the transit method here. You also want planets that are passing directly in front of the star or close to it for the radial velocity method, because then the star is moving directly towards you or directly away from you, versus otherwise the motions are kind of blurred out and you can't tell as well. So depending on where the star is, if it's up there, then it would need to be oriented directly at us like that. And so wherever it is in the sky, we need those rings of the orbits to be directly in line with our field of view. Otherwise, we're not going to be able to detect it with the transit method. So let me share this. Anyone who wants can play around with it. We're going to have lots of transiting planets here. So we'll clone it and just stick them all in this type of orientation, and we can see as many transits as possible. Transiting exoplanets this way. So we monitor tens of thousands of stars and can find tens of thousands of exoplanets. This method only works if the drop in brightness is big enough to detect, and it only works if they're lined up just right. So let's pull in our solar system model here. Moved around. Okay, here's a solar system model. Let's see if it comes in. Huh. This model for a little bit. Like we still have some people stuck in the elevator or the entry way. People stay stuck in there, then we can move back to the classroom if this isn't going to work. But okay. So let me talk for a minute about different exoplanet missions here. So we've got all kinds of space telescopes that help us search for exoplanets, and it is pretty amazing what they're able to do. The most useful one right now is TESS and James Webb Space Telescope. Let's pull in the James Webb Space Telescope, and not the... I know there's two models for it. Oh, there's Kepler as well. We'll pull in Kepler. So here's the Kepler Space Telescope. This one's a pretty awesome one. And let's pull in... Where did we go? No, it's here somewhere. Okay. I had it here. I feel like the update moved a lot of things around. Okay. Here we go. So here is the James Webb Space Telescope. We'll turn it around so we can see the mirrors and put it out there. Okay. So these are some of the cutting edge space telescopes. Kepler's a decade old now, but it just stared at one spot in the sky and was able to detect thousands of exoplanets. TESS, which I don't think we have a model of, is operating right now, and it is discovering thousands of exoplanets, but rather than focus on one spot, it is scanning the entire sky over its several years mission. And then the James Webb Space Telescope we use specifically for targeting the most interesting exoplanets and observing those, looking for signs of life. Okay. We're updated. Let's see. But first, here's an introductory video that should be good, I think. Oh no, it said it can't be played for some users in the session.
So I'm going to go with a cautious yes to your answer. Oh, here we go. Now we can have all the slides.
Thank
Look
you
at
so
that.
much. I'll read more about it later on.
So here's our planet, and it's going in and outside the habitable zone for a binary system. And I coloured it so that it's blue when it's cold, it's green when it's okay, and it's sort of yellow when it's on the edge. So you can see that it rotates and the stars rotate. And so the system's quite complicated when you've got a binary system here. And then finally, oh yes, we can play this movie. It was Loctite, it was airtight. But the airtight doesn't last forever. So they had 100 hours to find exactly where that sample had landed, collect it, bring it back to the airport, fly back to Japan, and have it safely stored in the curation laboratory. And they managed it in 60 hours. So the sample container came down, it came down in a parachute, And it had beacons, and there was also machine learning doing searches of the ground to try and find it. There were lots of different backups. And you see here, they're picking it up. At the bottom left, people are in protective gear. That's because in order to release the parachute, they actually detonated. There was like detonation releases to get that parachute up. And they didn't know for sure that they'd all detonated. So there was a possibility there might still be an explosive on that sample container. But actually, there was no problems. They picked it up safely. The top image shows the again.
Yes, this is Apollo 11. In fact. Let me just bring this.
Apollo 11. Yes. So Apollo itself is not particularly what I wanted to talk about. What I wanted to talk about is actually these craters. Now, the moon in the past did have some geology, but nowadays it's pretty dead. And as a result, you see a lot of evidence of this planet formation process because you see its surface is pockmarked with objects that have hit it. So if these objects were potentially bringing water, they would have landed not only on the moon, but on the Earth and all the other terrestrial planets. So this is why I thought this scene would be rather good. And also for what we're about to talk about. Let me just bring up my slides again.
Wait, could you repeat that, please?
Let us find one. Planet, spell planet correctly, and look for one of those. How about that one? Ooh, that's really big. I will scale that one down. Oh, no, wrong way. Oh, oh. Compromise, people. There we go. Oh, it's got a moon as well. Okay. So if we move this one right out here, so we'd expect this planet here to form mainly of dry grains and be a dry world, whereas this planet out here that's beyond the ice line is going to be forming from silicates and ices. And so we might expect it to contain a lot of water. And I can share these as well. Maybe. Translate, close. Yeah, that one too. All right. But here is the mystery. The Earth actually seemed to form sort of here-ish. Now, we know it doesn't have a lot of water, but it certainly isn't a dry planet, or we wouldn't be here. So what is going on? How is the Earth forming inside the ice line, but forming dry? In fact, in short, where did our water come from? Why do we have any at all based on this planet formation theory? And there are a number of answers. The first one is that this ice line that sits between these two planets about here wasn't always in this position. Now, this is actually quite likely because the sun would have been much dimmer in the past. And as it was cooler, the ice line would have been closer to it. So in that case, if we move the ice line to sort of this position,
levels with the rest of the stars around the galactic center. And of course, that bubble keeps us away from a lot of the cosmic rays that are so damaging to humans in space. Also, cosmic rays produce a lot of other effects, seeding clouds and changing our DNA and doing a number of things if you really get impacted by them that many are thinking that are important for the evolution of our species. So the astrosphere might be the beginning of the understanding of how life can survive on planets. So that's being investigated by a number of researchers right now. Thank you.
thank you.
We're talking about the bubbly, gassy thing that was recorded in the video, right?
2% water. Instead, most of the water in our solar system is out past the asteroid belt, where the giant planets are, many of which have these really icy moons with large subsurface oceans. So the question I want to answer today is why? So to understand that question, or at least to try and answer it, we have to go back and ask how. And for that, we need to take a look at the galaxy. So this is not our galaxy. This is M51, but it's a galaxy similar to us in that it has a very large spiral. And if you look at the spiral, you'll see that's where most of the stars exist and form. And if you zoom into that spiral, you start to see large clouds of gas that we call the giant molecular clouds. And inside those are star-forming regions, such as the Orion Nebula. Now, this movie is going to be very disappointing. Theatre, or at least I'm going to try. So this is the Orion Nebula. And through we go. So it's a large area of gas and dust. And inside those, you have super dense regions. And this is where our stars are going to form. I'm getting a bit of crackling. Could everyone make sure they're muted? Jim, I think it might be your fault.
Well, all I can say is, wow, I'm just looking around.
This was developed by the Hubble Space Telescope team at the Space Science Institute in Baltimore. It's absolutely amazing they made this 3D. Here we go, right into the star formation part. Where you can see a whole host of stars forming. All right.
Maybe this is too big. Yeah. So as soon as, well, this is not, of course, up to scale, because in fact it will be just something like this, and then Pluto will be something super small that we couldn't even see. But as soon as, right, New Horizons leave the Earth, it starts orbiting the Sun. The center of mass of its orbit is located on the Sun, and then it arrives to Pluto. So when a spacecraft leaves the Earth to go to somewhere else within our solar system, it starts orbiting the Sun. The center of mass of its orbit changes to the Sun, right? This is key to remember. And if you guys plan to study any engineering class related to orbital mechanics, remember, as soon as the spacecraft leaves the Earth, it starts orbiting the Sun, okay? Cool. Now, let me let's talk about the inclination. Every orbit, guys, has an inclination, and the inclination depends on the mission. Remember, guys, yesterday when we were talking about the spacecraft design, that that I don't have a spacecraft if I don't have a mission, and I don't have a mission if I don't have a payload. Well, there are more key points towards that statement. What happened? What if I want to launch an Earth observation mission that needs to take images of basically the squares? This is a little bit more like mathematic, but the squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axis of their orbits. Basically, Kepler's third law implies that the period for a planet to orbit the Sun increases rapidly with the radius of the orbit. So basically, this means that sorry, I think I lost my voice for a second. Basically, this means here, the squares of the orbital periods, for example, here, you see like the years. Mercury is 0.24 years, basically, that's like 88 days. It's the cube of its distance to the sun. Now, let's talk about the Newton's law of universal gravitation. I'm pretty sure is basically that you can describe the Keller's three laws of orbital motion. We are hoping that you also describe Newton's law of gravitation, and then maybe you can explain the different types of orbits used by Earth observation satellites or communication satellites, and then you basically can draw and label the basic orbit diagram. The outline, it will be similar to the learning outcomes. Basically, we will be talking about the Kepler's three laws of motion. We're going to talk a little bit of Newton's law of universal gravity. Like the type of orbits that we use for Earth observation. What are the unusual orbits? What are the the special locations? For example, where is the James Webb Space Telescope located? Well, it's in a Lagrange point, and in fact, that's a special location. So we know further ado, let's start with the Kepler's first law of gravitation. Somebody remembers from
government, but this is really a handbook for governments on how to build a space economy for the development and benefits of new non-spacefaring nations. So these two books, and there are other books that have been published over the last 2 years, Literature on Commercial Space, that basically describe the opportunities of this business in much more detail. So the opportunities of commercial space for companies, as I mentioned, for entrepreneurs, for investors, for students, we saw examples for students, and for countries alike. So how is this going to develop into the future? And I'm getting towards the end of my lecture. So that was built and subsequently launched by students, and that triggered the interest of the government, who used that as an example to the industry in their country to say, hey, we have people here who can build satellites. We are now suddenly a spacefaring nation. Let's build an infrastructure around that to stimulate this and keep these people, these very smart people, in our country to help. Nice guy, but it's an amazing story. The same happened in Mauritius. I was in Mauritius a few years ago, where again a university started to build a CubeSat that was subsequently picked up by the government and turned into the first Mauritian satellite that was very proudly launched with the Mauritian flag on it. But again, it was a student initiative. Costa Rica, another example where students started the space movement that was then picked up by the government later. And Costa Rica is now a great example of a Central American country that is leading in Central America in space. Again, based on students. And in Saudi Arabia, you probably know more about the Saudi Arabian